Hello everyone. I'm going to do this in 3 videos. You guys are going to see one per each page. I'm going to just take a look at the Chapter 5 test review and work through these problems kind of right along with you. So I'm going to zoom in here and we're going to start with the first one. Like I said, this is going to be the first of 3 videos. We're going to do one page at a time, so I'll try to keep these brief. Here, it's important to know what you're doing, right? So in this case, we are simplifying, right? So we need to do what we can until we think we are done. So on number 1 here, I don't like secant and I don't like cosecant. So my first move here would be to rewrite secant from the denominator in the numerator. That's going to create cosine squared A. And then doing the same thing with my other term, cosecant is the reciprocal of sine. And now I get sine squared A. Now that rings a bell to me. That is one of our cosine double angles. So we can simplify this down to cosine 2A. That's as simple as we can get. Let's look at another one. Here's number 2. And again, this seems familiar to me. I see that 1 minus 2 cosine squared, but it's not quite right. I know that cosine of 2b is 2 cosine squared b minus 1. So if we were to factor a negative 1 out, we would create that exact identity. So now I'm going to replace 2 cosine squared b minus 1 with cosine 2b. Like the first one, it's all about recognizing these formulas, these identities in the wild. Let's move on to a similar problem on number 3. Now there's some things I like about this problem and there's some things I don't. Right? I see the sine times cosine of an angle, and even looking at the angle, we see its denominator is 12, so I'm thinking this might be something like a double angle. However, this 4 right here is a little different. I know that the sine of 2a is 2 sine A cosine A. So basically, I'm going to rewrite this as 2 times sine, what ultimately ends up being A times cosine A, and we've created the sine double angle. All right, so this 2 is still going to be there, but we can replace 2 sine A cosine A with sine 2A. Now in this case, A was 5 pi over 12. If we were to double it, that would give us 5 pi over 6. Now we know that we actually can find the sine of 5 pi over 6. We know that it is 1/2. So all of that work leads us to the conclusion that for sine of 5 pi over 12 times cosine of 5 pi over 12 is just 1. All right, let's keep moving here. On to number 4. All right, now let's take a look at number 4. As I approach this, I see it's another simplified problem. I don't have, one equals 2, so I can't work on one side or the other. All I can really see here is the sine of 2x and the minus 1. I'm going to create a common denominator, and I'm going to use my double angle. Right? I'm going to do both those things as my first step. So I'm going to write this as 2 sine x cosine x plus cosine x. Well, the common denominator of 1 is going to be cosine x, so minus cosine x all over cosine x. And now I can see there's going to be some simplifying here. I can see that these will cancel, as there's one positive and one negative. And then I have cosine x divided by cosine x. Well, they will also cancel. So when this is all said and done, our simplest form will be 2 sine x. All right, one more problem on page 1. Oh, excuse me, there are 2. It looks like we do get a verify problem here. So I'm going to work on that messy looking left side, and I'm going to distribute it. I'm not sure exactly what's going to happen, but I have a feeling that some things are going to start falling away because I have negative sine y, positive sine y, positive cosine y. More than anything here, I'm just going to see what happens, right? 1 times 1 gets us 1. 1 times sine gets us sine y. 1 times negative cosine y gets us negative cosine y. Our second distribution here, I'll just change colors. Negative sine, we're going to have a minus sine y here. We're going to have a minus sine squared y. And we're going to have a plus sine y cosine y. And then for our third batch of distribution, I'm just going to change over to blue here. I get a positive cosine y. I get plus cosine y sine y. And finally, I get minus cosine squared y. I'll put this over here. So I'm going to combine all my like terms here and rewrite as a single expression. Well, let's start. Well, the sine y's cancel. The cosine y's cancel. So let's say negative cosine squared y minus sine squared y plus 2 sine y cosine y. And in my head, I'm feeling pretty good about things because that 2 sine y cosine y is very much what the sine double angle looks like. So now I need to deal with the cosine y and sine y. Well, I know that sine squared is the same as 1 minus cosine squared, right, with a Pythagorean. All right, if I were to take negative cosine squared y minus that, I would have, well, now I have a negative cosine and a positive cosine. Oh, you know what? I dropped my 1 as well. There should be a plus 1 here. And what we can see is that this minus 1 will cancel with that plus 1. That plus 1 I overlooked was right there. So when it's all said and done, all the other stuff has canceled, and we're left with 2 sine y cosine y, which is the same as the sine of 2y, which is where we were going. So in this case, we distributed, and we were able to cancel quite a bit. All right, guys, one last problem here. All right. Now we have negative 2 cotangent x equals sine x over 1 plus cosine x minus 1 plus cosine x over sine x. I'm not sure where we're going to end up, but my first instinct on a problem like this is to create a common denominator. I'm going to create that common denominator by multiplying by the other denominator in the problem. I'm going to create sine squared x minus 1 plus 2 cosine x plus cosine squared x. Good. So now what I can do is I can start rearranging things. I know that if I'm heading towards negative 2 cotangent x, I know cotangent x is, I could expect something like this as my second to last step. So I kind of like seeing that 2 cosine x in my numerator. Now I got to deal with all the other stuff. So I'm going to rearrange things, and I'm going to write that numerator as sine squared x minus cosine squared x minus 1 minus 2 cosine x. Now as I look at this numerator, I can do some simplifying. I'm looking at the sine squared minus cosine squared. Well, I know that sine squared x plus cosine squared x equals 1. And I think what I want to do is I'm going to replace sine squared x. So sine squared x is the same as 1 minus cosine squared x. So we could say 1 minus cosine squared x minus cosine squared x minus 1 minus 2 cosine x. Well, still working in the numerator here. Don't forget, we do have that denominator. I will come back to it. I'm just working in that numerator. So the next step, I would combine my like terms. I have negative cosine squared minus cosine squared. So there's negative 2 cosine squareds. I also have 1 minus 1, which is 0. And believe it or not, we're almost home. So what we're going to do as our last step, our second to last step, is we're going to factor negative 2 cosine x out. And what will be left is cosine x plus 1, which I'm hoping you remember was part of our denominator. Now I have cosine x plus 1 with 1 plus cosine x. I can cancel those. I can see that what remains is negative 2 cosine x over sine x, which is the same as negative 2 cotangent x. That's what we're after. So that's our first of 3. Stay tuned for sections 2 and 3. All right, guys, so this is going to be part 2 of our 3-part series working through our review. I'm picking up at number 7. If you need to see the first page, just check the previous link. All right, so here on number 7, we have quite a bit to do. We are going to find sine a plus b, tangent of 2b, and tangent of b over 2. So what that's going to look like, ultimately what we need to solve these problems is this. Sine of the first angle, cosine of the second, plus sine of the second angle, cosine of the first. So I'll need some information. I don't have a lot of that. A number 8, tangent of 2b, tells us this is going to be 2 tangent b over 1 minus tan squared b. And then everyone's favorite is the tangent half angles. I would prefer to avoid these ones when I can. I never seem to remember. But in this case, I think using 1 minus cosine b over sine b is going to be our best bet. So that's what we need to solve all 3 of these problems. I need, well, tan of b, I might have what I need here, just from the problem itself. Sine and cosine, I don't have quite what I need. So I'm going to need some extra information. So in the problem, they tell us that angle A is in the first quadrant, and it's got a tangent of 4/3. So that's going to look like this. There's angle A. The hypotenuse would be 5. Triangle B is also, angle B is one that we'll need a triangle for. It is between 180 and 270, meaning that's quadrant 3. So there's angle B. Its tangent is 12/5, but because we're in the third quadrant, we know those are both negative. Well, now we have quite a bit of information, right? We have those 2 triangles. So when we plug in for the sine of A and the cosine of B, we're going to use those triangles that we've just created. So the sine of A is 4/5. The cosine of B is negative 5/13. We're going to add to that. Well, sine of B is going to be negative 12/13. And the cosine of A is 3/5. From here, we're just simplifying. So we end up, we know our denominator is going to be 65. We get negative 20 plus negative 36 all over 65 for an answer of negative 56 over 65. There's our first one. All right, next we have to find tangent. I'm going to go to another color here just so we can not get too bogged down. I'm going to plug in what I need. So I need 2 times tangent B. Well, I already have tangent B, so it's going to be 2 times 12 over 5 divided by 1 minus 12 over 5 quantity squared. So we're just simplifying this fraction. We get 24 over 5 over, let's see, Let's do 25 25ths minus 144 over 25. We can do some simplifying kind of on the fly here. We could reduce and reduce. And when it's all said and done, we end up with 24 divided by, oh, sorry, those should have been 5s, my mistake. And we can kind of go from there. When it's all said and done, we end up with negative 120 over 119. All right. So let's move to the third one. Here we have the tangent of b over 2. So I'm using 1 minus cosine b over sine of b. Nothing really specific about that one that I love, other than the denominator's not as complicated. And I know that from these, I'm going to have some kind of weird looking denominators. So I'm going to plug in here 1 minus, well, the cosine of b was negative 5/13. And the denominator was the sine of b. Well, the sine of b was negative 12/13. This is the same as 1 plus 5/13. So that's going to be 18 over 13 over negative 12 over 13. Well, when we have those denominators that match, we can cancel them. So we have 18 over negative 12, which is the same as negative 3 over 2. Guys, when we see these problems, right, when we see problems where they're telling us about quadrants, where they're telling us about the signs of certain functions, they're really telling us that we have to build some triangles. Once we have those triangles, we can use our formulas to plug in for what we need. And then that moves us into our equations, all right? So as we look here, number 10, right, we're going to solve for all x's between 0 and 2 pi, right? All x's between 0 and 2 pi. So this first one is pretty direct. I have the sine of some angle, and that angle has a sine of root 3 over 2. I'm very happy to see root 3 over 2. That is a unit circle value, so I can use that to my advantage. Well, when I think of the unit circle, I think sine is positive on the top and negative on the bottom. I know root 3 is relatively close to the top of the unit circle. So the two locations on our unit circle where we have a sine of root 3 over 2, well, those are going to be at pi over 3 and 2 pi over 3. To solve, I'm going to turn x over 2 into x. I'm going to get that by doubling both sides of the equation. My final answers here will be 2 pi over 3 and 4 pi over 3. Let's look at another one. So here's number 11, and I have a problem here. The problem I have is that I have cosine of 2x and sine x. Having those two different trig functions is going to make factoring this one a little bit more of a challenge. But I know that cosine 2x looks a few different ways. It can look like cosine squared x minus sine squared x. It can look like 1 minus 2 sine squared x. And it can look like 2 cosine squared x minus 1. So I have some options. And the issue I'm trying to resolve is that I have non-matching trig functions. Well, this first one doesn't make any sense because it won't solve that problem. And replacing cosine with cosine will also not help. So what I'm going to do is I'm going to plug in 1 minus 2 sine squared in for cosine 2x. Well, now I'm going to rewrite this in reference to 0 because this is going to be solvable through factoring, and we always want to set our equation equal to 0 before we do so. So I'm going to move everything over to the right side of my equation. That's going to flip the signs, SIGN signs, minus sine x. And then I had a 4, which becomes negative 4. So this is a familiar setup at this point. I'm going to solve through factoring. right? And the zero product property will get me to my answer. I know that 2 is prime, so 2 sine x and sine x will be in my lead positions. The minus 4 will plug in here, and the plus 1 will plug in there. So we've solved here, we've factored, and now we can solve. We need to figure out where sine of x equals negative 1/2 and where sine of x equals 4. If that sounds a little fishy to you, this factor here will not create a solution, right? Sine of x can equal 4, so there's no answers that come from that factor. Our final answers here are going to be the locations where sine of x equals negative 1/2. When I think of sine, I know positive on the top, negative on the bottom, and 1/2 is going to be relatively close to the x-axis. Those two angles will be 7 pi over 6 and 11 pi over 6. All right, we got a couple more here. Let's see, we got 12 and 13 to finish up. So here, I want to think about what makes this problem a challenge right now. And what I see is that 4 in front and the sine squared. So I don't really like the 4 or the sine squared, so I need to find a way to resolve that. So, sine squared of our angle, x plus pi over 6, will equal 1/4. And then we take the square root of both sides, so sine of our angle will equal plus or minus 1/2. All right, that's reasonable for us. We know that 1/2 shows up on our unit circle. Now, we do have the last complication here is the x plus pi over 6. That's just going to be a horizontal shift to our graph. So at the end, we will have to subtract our answers. So let's list out. So x plus pi over 6 is going to be all the locations where the sine of the angle is positive or negative 1/2. That happens at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And just to be safe, let me see where our answers were. All x's. Now, usually with our solution set, we would include 0 but exclude 2 pi. I'm just planning ahead on that one. So our final step, getting x by itself, we will subtract pi over 6 from each of these 4 answers to get our ultimate answers. It'll be 0. 4 pi over 6 is 2 pi over 3. We'll get pi, and we'll get 10 pi over 6 or 5 pi over 3. And there are our 4 answers. This is a problem we're working backwards, right? In our reverse order of operations is how we want to operate. Final problem on the page, let's look at 13. We see sine 2x minus 2 cosine x. And while we have 2 functions, the bigger headache that we're going to have to deal with is the 2x, right? These are different 2x's, right? This 2 is multiplying x. This negative 2 is multiplying the cosine. So we do have to treat them differently. In the problem up above, we had multiple options for cosine 2x. In this case, we only have one. Sine 2x always is rewritten as 2 sine x cosine x. And now I can see a common factor or 2 here. So I'm going to add 2 cosine x to the other side so that I can solve through factoring. What I notice here is that there's a 2 in each term, and there's also a cosine x in each term. So I'm going to factor out 2 cosine x, and I'll be left with sine x plus 1. Well, now I'm in factored form, and this is the one situation where having 2 different trig functions can work. The only way we will be able to factor something like this is through GCFs. So let's solve it. Cosine x must equal 0, and sine x must equal negative 1. Well, cosine x equals 0 at pi over 2 and 3 pi over 2, right along the central axis, the vertical central axis of the unit circle. Sine equals negative 1 at 3 pi over 2, so that's a repeated answer, but those would be our solutions. Thanks, guys. We'll have one more video to look at the calculator section.